Hi there, welcome back to the new video. So today we'll be going through this paper which is titled as LSBert, a simple framework for lexical simplification. This came out in the year of 2020 in the month of June. Okay, so let's bifurcate the title first. So they have named their work as LSBert, which can be seen as lexical simplification using BERT. Then the next question arises, what is lexical simplification? So lexical simplification is the subwork that is done in the domain of text simplification. In lexical simplification, we majorly focus on replacing complex words that occur in a sentence, and with this technique, we try to simplify a sentence. Unlike in text simplification, where we focus on other aspects as well, such as simplifying the grammatical structure, dealing with the complex word, and so on and so forth. Okay, so with this idea in mind, let's read the paper. Lexical simplification aims to replace complex words in a given sentence with these simple alternatives of equivalent meaning to simplify a sentence. So this is exactly what we discussed. Recent unsupervised lexical simplification approaches only rely on complex word itself, regardless of a sentence to generate candidate substitutions. Okay, so what they are saying is the current unsupervised lexical simplification techniques focus just on replacing complex word regardless of which context it occurs in, which produces large number of spurious candidates, which is bound to happen. Because unless you consider the full context in which a word occurs, you'll be missing out on polysemic words. Which means let's consider a sentence as I have put my money in bank. Let's say this is a sentence that we have, and somehow we come up with the conclusion of doing a lexical simplification on this word, which is bank. So now if you don't consider the context that has occurred before this word, so there exist two possibilities in which the substitution could take place, where one is in the context of river bank and other is in the form of normal bank, where we deposit our money. So the previous techniques didn't focus on context at all and would directly start replacing words that are synonymous to bank, which is bound to give you a large number of false positives. Okay, so they say we propose a lexical simplification framework LSBert based on pre-trained representation of the model BERT that is capable of making use of wider context when both detecting words in need of simplification and generating the substitute candidates and taking 5 high quality features into account for ranking the candidates. Okay. What they are saying is the technique this paper proposes is based on BERT, where they try to come up with the replacement of certain word in a sentence, let's say bank in this case, by considering the context in which that word occurs. So as you might already be familiar with what BERT is and how does it work, you might have already guessed this is going in the direction of masked language modeling, where we try to predict all the masked words in a sentence using the context words. They say when compared to the baselines, they outperform the current state of the art by 29.8 accuracy points, which is huge. Okay, let's move forward. So they say the LS framework is commonly framed as a pipeline of 3 steps: complex word identification, substitution generation of complex words, and filtering and substitution ranking. Complex word identification is treated as an independent task. Existing systems mainly focus on 2 steps, which is substitution generation and substitution ranking. Okay, so authors have proposed a 3-step mechanism. So given a sentence, let's say this is a sentence that we have. First task is to identify complex word identification task, where they would identify which are those complex words which they need to replace. Once you have those words, the next task is substitution generation, which accounts for generating similar words that could be replaced at that position, which are simple to comprehend. So once the substitution generation step is done, they talk about doing a substitution ranking. So you'll be having a list of candidate words that could be replaced at that position. So how do you rank and choose the best one that should be replaced at that position? So this is what they're calling as substitution ranking. And then they mention the existing systems which are present today don't go about doing a complex word identification task and just focus on the generation and the ranking step. Okay. So if we focus on this figure, we see if the sentence was John composed these verses, the model identified the word composed and verses as the complex words that need to be simplified. So the above table represents 3 models, the LSBert what the authors have proposed, and these 2 were the existing state-of-the-art models. For the word composed, the LSBert was able to generate these 3 words which were wrote, created and formed. Whereas if you compare it with the remaining two models and what they have produced, the generations don't seem to be simple and coherent. And similarly, in the below table, the example is for the word verses. The LSBert generates three words, which is poems, speeches, and lines, and these are from the other two models. So this is the table that shows the results after you have done substitution for both the complex words. The LSBert came up with John wrote these poems, whereas these are the samples generated by remaining systems. So it's clearly visible like LSBert has a bit of a lead in terms of doing simplification. And that's what the authors also mentioned in the abstract. When they compared it with the baseline and existing state of the art, they were performing better. Okay, so let's move forward. So in this diagram, authors have pictorially tried telling about each of the steps that are involved in doing the simplification. So you have some original sentence, which is John composed the verses. The first step is to do the complex word identification. So let's say a model says composed and verses are two of the words which are complex, and these are their respective probabilities. So it's clearly visible. Verses is much more complex compared to the word composed as per the model that they have trained. Once this step is done, they proceed to step number two, where they generate the substitute for the word verses. So these are the words that they have got. Once they have got the candidate substitutions, they go about doing a filtering and a ranking step. Post that, they substitute the highest rank word with the complex word. So if you notice, this full pipeline of four steps was just done for the word verses, and this again repeats. That's why they have written recursion, and this repeats again for the word composed. So now you can see the verses word has been already been replaced by poems, and now again all the four steps happen to replace the word composed. So in the fourth step, you replace the word composed with the word wrote, and finally you get a simplified sentence, which is John wrote these poems. So this is the full algorithm to how things are happening. One main thing to notice in this approach is that for every complex word that you identify, you run all the remaining steps and do a substitution for that, then do it recursively for all the remaining complex words that you have already identified. So yeah, now let's dig in the detail of each of the four steps and see what is the mechanisms and what models are authors using. So they mention LSBert simplifies one complex word at a time and is recursively applied to simplify the sentence. So this is exactly what this recursion step was doing. Okay. They frame this task of complex identification word in the form of a sequence labeling task, for which they use BiLSTM, that is trained to predict the binary complexity of a word given an annotated dataset. Okay, so this is similar to how named entity recognition or any sequence labeling task is done. So what happens is the training dataset consists of multiple sentences, let's say S1 to SM, and each of the sentences is nothing but a sequence of words, let's say W1 to WN. And you're also given one label for each of the word. In case of named entity, it would be either person name, location, ordinal, cardinal, all of those categories. So in this case of complex identification, you'll be given a sequence of words that belong to a sentence, and for each word, you'll be given whether it's a complex word or not. So essentially, two labels. So considering if this was a sentence that we had, so the training dataset format would have been not complex, complex, not complex, and complex. Then you would train a model that would take this sequence of words as an input and outputs these sequence of tags. Okay, so that's what they have written. The approach labels each word with lexical complexity score P, which represents the likelihood of each word belonging to the complex class. So that is the probability that you get after sigmoid. So that is the score that they're talking about. And then you have some predefined threshold P. If the lexical complexity of one word is greater than the threshold, it will be treated as a complex word, which is actually how a sigmoid works. If you have a threshold of zero point 0.5, any number that you get above zero point 0.5 after putting in the sigmoid, you make it 1, otherwise you make it as 0. For the sentence John composed these verses, we got the score 0.55 for the word composed and 0.76 for the word verses. And they had set their threshold value to zero point 0.5. LSBert starts with the word verses with the highest p value above the predefined threshold to simplify. Okay, so the model starts by picking the word that has the highest probability first. And after completing the simplification process, which was all the three steps in the pipeline that we had talked about, we recalculate the complexity of each word in a sentence, excluding the words that have been simplified. Okay, so if you see this diagram, what they're saying is Once you're done with the replacement of the word versus in its simple form, which is poem, we then again perform a complex word identification task because the word in a context has changed. So now if you see, 0.63 was the probability that you get for the word composed. Initially you were getting 0.55. And then you perform all the remaining steps. In case your model again encounters the replaced word as a complex word, you ignore that. That's what they have written. We exclude the word that have already been simplified. And they also exclude any simplification on the entity words that exist in that sentence, which could be any name of a person, any location, any company name, and so on and so forth. Okay, so this was about complex word identification. Talking about substitution generation. Given a sentence S and complex word W, the aim of the substitution generation is to produce a substitute candidates for a complex word W. LSBert produces the substitute candidates of complex word using pre-trained language model BERT, and then they summarize what BERT does. So yeah, this is pretty straightforward to how do they generate the substitutes. I've already made a video on how BERT works. I'll link that video in the I button. Do check out the description of that video and go to the relevant timestamp. But just to summarize in 15-20 seconds to what is happening over here, let's say I have a sentence S, which is lexical simplification framework. So this is the sentence that you have that has 3 words. Once you are done with the complex word identification task, let's say this was the word that was identified in the process. Treat this as masked word now and come up with a replacement of what has to be put over here, which is a typical task of masked language modeling on which the BERT was trained, in which it would consider all the context words that occur around it and come up with a word that could be replaced at this position. So this is exactly what they are trying to do in this substitution generation task. So at the output, you'll be getting a softmax distribution across full vocabulary. Okay, moving forward. So coming to this diagram, here we can see the exact working of the substitution generation model. So you input the original sentence S, which was the cat preached on the mat, and then you put a separator token. And since preached was identified as complex word by our complex word identification model, we put a mask at that position and append that sentence post we have put a separation token. So now to a BERT model, we have two sentences. One is the original sentence and other is the masked sentence. And at the output end, we would want a possible substitution for this masked word, which is this, what they have generated. So this is how typically BERT works. Although one thing to notice in this approach is that the authors also input the original sentence along with the masked sequence. And the reasoning that the authors have given is that while you're trying to predict the masked token sequence, it would attend to all the sequence words that occur in that context. So model could attend to the original word for which we are trying to generate the substitute and also the context in which that occurs. So that is the reasoning. Okay, moving forward. So filtering and substitution ranking is the final step in the simplification pipeline. Given a substitute candidate C from C1 to Cn, so you have n candidates. The substitution ranking of the lexical simplification framework is to decide which one of the candidates that fits the context of complex word is the simplest, where n is the number of substitute candidates. Threshold-based filtering is performed by LSBert, which is used to remove some complex substitutions. So they do some kind of threshold-based filtering to remove some complex words using their zip values from frequency features. Okay, so let's see what these frequency features are first. Frequency-based candidate ranking strategies are one of the most popular choices by lexical simplification and are quite effective. In general, the more frequency a word is used, the most familiar it is to the users. So the hypothesis they are building is if a word is commonly used across the language, it has to be relatively simple compared to a word which is not often used. So zip frequency of a word is nothing but the base 10 log of number of time it appears per billion words. And they use this corpus, which is subtlex, as the corpus against which they calculate the zip frequency. Because some of the experiments reveal the word frequency from this corpus correlate with the human judgments of simplicity. Okay, fair enough. Let's move forward. Then they talk about computing various rankings according to each of the features and then finally averaging all the rankings to get the final ranking. And from that, they pick the highest ranking word as the best substitute. Now let's dig into each of the features which they are using for the ranking purposes. The first is BERT prediction order. On this step of substitution generation, we obtain the probability distribution of vocabulary corresponding to the masked word. So that is what I was talking about. You get a softmax distribution across the full vocabulary. And because LSBert already incorporates the context information on the step of substitution generation, the word order of the BERT prediction is a crucial feature which includes the information from both context and complex word itself. So the higher the probability, the more relevant the candidate is for the original sentence. Okay. Then they talk about language modeling feature that essentially takes into the consideration that the grammatical structure after you have replaced a simple word with a complex word still remains intact. That's what they say. We cannot directly compute the probability of a sentence or sequence of words using BERT like traditional n-gram language models. So they define capital W to be this sequence, where W is the original word, and these are M words to its left, and these are M words to its right. They come up with a new strategy to compute the likelihood of W. So the likelihood of a sentence would mean how likely or probable this sentence is in terms of its construction in context of rules from some language, let's say L. They say we first replace the original word W with the substitution candidate. We then mask one word of W from front to back and feed it to BERT to compute the cross entropy loss of the masked word. And finally, we rank all the substitute candidates based on the average loss W. The lower the loss, the substitute is a good substitution for the original word. Okay, so what they are saying is you have a sentence S that has n words, W1 to Wn, and let's say W5 was the word that was identified as a complex word. So you find a substitute for that word using BERT. Let's call it WS. So the way they would calculate the likelihood of a sentence is the first step that they talk about is replacing each of the candidates. Okay, so this is essentially the list of candidates. So they talk about replacing each of the candidates with the complex word. So let's say if we replace with the first candidate word, so our S sequence becomes this. So now what they do is from each of the words from starting, they mask each of the word and pass it through a BERT and calculate the cross entropy loss for that masked token. So let's say for the first word you get as CE1, and similarly you'll be getting for all the n words one by one. So then you take the average. So this is your final average cross entropy loss for that sentence, which resembles the likelihood. So you'll be getting one score per candidate. So finally, if you have k candidates, you'll be having k of these losses. So you arrange them in the descending order and pick the top one, and that is your ranking. So this is pretty intuitive and looks correct because if WS1, which was one of the substitutes, is not that good, let's assume. So now if you start calculating the cross entropy loss for each of the word in that sequence, you're supposed to have little high scores because the prediction at every step would depend on all the context words. And if one of the words is not good enough, the model will be confused regarding the prediction at any position. So by this, good candidates should have low on average cross entropy loss. So that is the idea, what they propose. And they mention they use a symmetric window of size 5 around the complex word, which is 5 word to its right and 5 word to its left. Okay, now talking about semantic similarity, which is a very intuitive and common strategy to look out for. They use pre-trained fast text model to get the word embedding for the complex word as well as one of the substitutes, and whichever has highest cosine similarity is ranked higher. Okay, let's move forward. So the final feature that they use for ranking is called PPDB, which is an acronym for paraphrase database. So PPDB is a collection of more than 100 million English paraphrase pairs. So a paraphrase pair would mean two sentences talking about exact same thing but are rewritten in different format. These pairs were extracted using bilingual pivoting technique, which assumes that two English phrases that translate to a same foreign phrase would have the same meaning. So let's say you have a lexical unit L1 and another lexical unit L2, where each of L1 and L2 could be either phrases or words or sentences. So if you do a translation of both of them to some common language C, if both of them come out with the same output, then you say L1 and L2 are paraphrase of each other. So this is the core idea behind how PPDB database was built. Considering PPDB owns useful information about paraphrase, we try to use this as a feature to rank candidate substitutions. We adopt a simple strategy to rank the candidates for each candidate CI in capital C of W. So W is the complex word. After it goes through BERT, you get n candidates. So each of them is called CI. So the ranking of each of the substitute is 1 if the pair of word and substitute exist in the database. Else otherwise, the ranking is decided as n by 3, where n, if I remember correctly, they have mentioned to the total number of substitutes what they have. So this is the ranking mechanism that they employ from PPDB database. Okay, so I guess we are done with the paper. Now they have the experiments and all. So they have two algorithms written over here, which is exactly the same thing that we have already discussed. So I'll not go through that. So we are done with the paper now. So if you like such content, make sure you hit the like button, subscribe to the channel, and do share it with your friends. We'll meet you in the next video. Bye bye.